Hello everyone, welcome to Nature Academy. Myself Dr. Shaik Ahmed. In this lecture, we are going to learn some important topics in quantum mechanics. For example, blackbody radiation and the distribution laws, which tries to explain the blackbody radiation. So about myself, I have completed my PhD from University of Hyderabad in theoretical physics. I am a CSIR JRF and also qualified GATE. I have 8 years of teaching experience at various levels, graduate, postgraduate levels. So today's topic is about blackbody radiation and the contents are here listed below. First one is Stefan Boltzmann law. We'll discuss what is Stefan Boltzmann law and where this scientist Stefan and Boltzmann failed to explain the blackbody radiation. That thing also we can discuss, and followed by Wien's energy distribution and Rayleigh's energy distribution functions, and finally we'll work on Planck's radiation law. Okay, so let us start with blackbody radiation. What do you know about blackbody? What do you mean by blackbody? Blackbody is perfect absorber and perfect emitter. So let us try to give an example for that one. So blackbody is in daily life. I can give one example for the blackbody, that is a cavity with a small hole on the surface. Cavity is nothing but, you can say, it's a mirror. Okay, mirror can act as a cavity. So for example, if you have a cavity like this and it has some hole here, you can look at the small hole here, and if you send some radiation through this hole, this radiation will enter this cavity and it will make so many reflections. Okay, and I can say that the radiation is trapped inside this cavity. Now I can treat this hole as a perfect absorber of radiation, since it is absorbing radiation. Okay, so the hole on the surface of this cavity is absorbing the radiation, so I can treat this hole as a perfect absorber. Now if the hole is heated, assume that the hole is heated, then what happens? So for this you have to apply some uniform temperature. Now we try to heat this cavity. Okay, that means you are giving a uniform temperature to this cavity. Then what is happening to this cavity? So then you can see that whatever be the radiation inside this cavity, it will come out like this through this same hole only. Okay, so the radiation can escape through this hole. So then I can say that this hole is acting as emitter of the thermal radiation. Initially it was an absorber, now it is an emitter. So I can say that a perfect absorber or perfect emitter is an example for a black body. Okay, so the radiation is contained inside the cavity. Then how will you characterize the radiation? So for example, if you want to define anything, you should have some characterization, right? For example, if you want to discuss the particle motion, so particle nature, if you want to discuss the particle nature, then the particle must be characterized by its mass or its velocity or both. And if you want to discuss a wave, then a wave is characterized by some properties like amplitude or wavelength, or you can say it phase, frequency or phase. Anyhow, the wavelength and frequency are both are related to each other. So at least we need some parameters like amplitude and phase are required to describe a wave. In the similar way, the blackbody radiation is characterized by energy density. So what is energy density? So energy density is nothing but energy per unit volume. Okay. For example, if you want to describe mass density, what do you mean by mass density? Mass per unit volume. Charge carrier density, charge per unit volume. Molar density, number of moles per unit volume. So in the same way, I want to discuss the energy density. So U of nu comma T is my energy density here. So how much energy is stored in this volume is known as energy density. So there are important things, important points. So sometimes you will get theoretical questions on this blackbody radiation. One is the energy density depends only upon the T, temperature of the object. So it is independent of the shape of the object and chemical composition of the object. So these 2 points are important in state level exams like your JL, junior lecturer and polytechnic lecturers, there may be a chance to ask a question on this concept. So the energy density of radiation. For example, we have radiation inside this cavity, and this radiation is characterized by some energy density U of nu comma T, and this nu of u comma T is independent of the shape of the cavity and composition of the cavity. It will only depends on the temperature of the cavity. So this concept, blackbody radiation. So in exam you will get so many questions, and all the questions are related to temperature only. If you look at the previous year's questions, there are so many questions, they are related, they are asking questions about the temperature only. If the cavity temperature is T, then the radiation will, energy density will be mu U. If what happens if the temperature is increased to T, then what happens to this energy density, or what happens to the specific heat, or what happens to the entropy of the radiation, like these things. Okay, so our intention is temperature variation of these properties. Okay, so now we can give one example for black body, that is a cavity with a small hole is a black body. Next, if you want to heat a solid object, then what happens? So the thermal radiation emitted by a black body or emitted by a glowing solid object consists of a continuous distribution of frequencies. This is an experimental data, students. Look at the shape of this graph. For example, I want to talk about the temperature when the temperature of the object is 5000 Kelvin. So this is the shape of the energy density function. You can look at the shape of the energy density function. With increase of frequency from here, starting from here, with increase of frequency, the energy density is increasing, and at a certain point it starts decreasing. Okay, so surprisingly, for different temperatures there are different frequency values. So this is the energy distribution function. So the peak of the radiation spectrum occurs at a different frequency, and that is proportional to the temperature. Look at here. So when the temperature is 2000 Kelvin, you can find the frequency is approximately 1 into 10 power 14 hertz here, and the temperature is raised to 3000 Kelvin, the temperature is changes to 1.8, the frequency is changed to 1.8 into 10 power 14 hertz, like that. So that means when you draw the energy density diagram as a function of frequency, with increase of temperature, the frequency is shifted towards the right side. Okay, the peak frequency is shifting towards the right side. Okay, so this is the underlying reason behind the change in the color of a heated object as its temperature increases, notably from red to yellow to white. For example, if you take iron or some other metal, if you heat it, initially the metal color will change to red. Further increase of temperature, the color will change to yellow. If you give further temperature, if you increase the temperature, finally the metal will change to white color. Okay, so why the metal is changing from red to yellow to white? Because the frequency is dependent on its temperature. If you increase the temperature, the frequency will change. If the frequency is different, the color will be different. Okay, so this is the energy density diagram with respect to frequency. And if you draw the same thing, energy density with respect to wavelength, you will get somewhat different behavior. So look at this one. The first graph is when the temperature is 2000 Kelvin. With increase of temperature, the lambda value is shifting left side. Okay, let me identify the peak values in both cases. The first case is this is the peak value when the temperature is 2000 Kelvin, and this is the peak value when the temperature increase, and this is the peak frequency when temperature is 300 Kelvin, and this is peak frequency when the temperature is 5000 Kelvin. That means the peak values are going like this. Okay, somewhere like this. This is in the frequency. This is this is for energy density as a function of frequency. So the peak values are shifting to right side with increase of temperature. Whereas if you draw the energy density as a function of wavelength, the frequency is shifting. So the wavelength, the maximum wavelength is shifting towards the left side. Okay. So the peak value of wavelength is shifting toward the left side depending upon these behavior. You know, right? Frequency is inversely proportional to 1 by lambda. So we can expect the same here, right? So these 2 points are very important. These graphs are important. We got 2 questions in CSIR for the last 3 years. Okay. So Stefan Boltzmann law, I will start with Stefan Boltzmann law. Stefan and Boltzmann, they try to give the expression for the total intensity radiated by a glowing object of a temperature T. What do you know about intensity? What is the definition for intensity? So intensity is total power per unit area. Okay, students. So intensity is given by power by unit area. So the formula is given by A sigma T power 4. What is A here? What is sigma here? What is T? I will write here. T is absolute temperature. Absolute temperature of a black body or a glowing object. Sigma is Stefan Boltzmann constant. The value, numerical value, is 5.67. 567 10 power minus 8. So they are in like 1, 5, 6, 7, 8 like this. So I'll write the units. What are the units will come later. And A is emissivity of the black body. So this is emissivity of the black body. If A is equals to 1 for perfect black body, I will write here perfect black body. BB represents here black body. Otherwise, the value is less than or equals to 1. Okay. And what are the units of sigma? See here. Here we have power by area. What is the unit of power, student? Power is represented generally with watt. Area is meter square. Okay. And emissivity is a constant value. No need to worry about it one. It's either 1 or less than 1. And what else here? So I can remove this one. Temperature is there. So I will get K4 here. So on the right side we will have sigma only. So the units of Stefan Boltzmann constant is given by watt, meter square or Kelvin power minus 4. Okay. So I hope you understood this thing. And next. So there is a question on this formula. Okay. Let me erase all these things here. So CSIR net 2019 and December. So you remember the formula, the total intensity emitted by a glowing object or power per unit area is equals to A sigma T power 4. Now there is a question. So let us try to answer the question. Consider a black body of radiation in thermal equilibrium contained in two-dimensional box. The dependence of the energy density on the temperature is. So what is the formula? So look at this one. Intensity nothing but total power by area. So I can treat this as energy density. So intensity and energy density and energy and radiation pressure, if you like all these components, they are proportional to T power 4 for a three-dimensional space. For 3D space, they all are proportional to T power 4. Okay. Or other words, I can write the intensity or the energy density, anything is proportional to T power D plus 1 here. What is D? D is the dimension. D is dimension. So Stefan Boltzmann derived an expression for energy density and intensity, and that is proportional to T power 4 in 3-dimensional. Okay, so if it is a 2-dimensional box, so substitute the value here. So for 2-dimensional, what will you get? D is 2, 2 plus 1. Therefore, the intensity, energy density, energy pressure, anything, they are proportional to 2 cube only. So what is the answer here? This one. Generally, students used to do the mistake. Oh, we know that this is the formula for Stefan Boltzmann. Yes, of course, this is the formula for Stefan Boltzmann, but there is a condition. This is Stefan derived this expression for a 3-dimensional object. So in 3-dimensional case, you will get T power 4. Okay, so I can write the formula as intensity is proportional to T power 4. Instead of writing T power 4, I will write dimension plus 1. Okay, if you in exam, for example, sometimes in I think 2016 December in say CSIR net, there was one question stating that asking the question related to specific heat and entropy. So if S represents the entropy, then there is a relation. Entropy is also related to your temperature. So how to remember this one? So I can write the entropy is proportional to T power the dimension. Okay. So if it is three-dimensional system, the entropy is proportional to T cube. If it is two-dimensional system, the entropy is proportional to T square. If it is one-dimensional, entropy is proportional to T1. Okay. Then what is the relation between specific heat and the temperature? So you know that specific heat is generally represented with the CV. This is also proportional to T power D, and there is one factor. If I write that factor as, you can take L, M, N, and S, anything. So this is okay. Don't take S here because S already used in entropy. So let me take this is as X. So X is equals to 1 for massless particles, for M is equals to 0, and X is equals to 2 for massive particles. Okay. For example, try to focus on the three relations. So there are so many questions in your CSIR, JEST, and local university exams, government job exams. They are asking questions on these three parameters only. One is intensity, energy density, and radiation pressure proportional to T power 4, that is proportional to T power D plus 1, and entropy is proportional to T power D, and specific heat is proportional to T power D by X. If it is a massless particle, X is equals to 1. What is the example for massless particle? The example for massless particle is photon. For photon, specific heat is proportional to T power D. If it is three-dimensional, I can write the specific heat contained in three-dimensional object is T cube. Either. If it is massive object, then it is T power D by 2. Okay, so this is very simple question. CSIR 2019 December. So answer is T power T cube here, since it is a two-dimensional, right? Okay, let us start with Wien's energy distribution function. Wien gave an experimental proof that the energy density of a black body, the energy density of the black body is given by the expression this one. Energy density U of nu comma T. That means energy density is a function of frequency and temperature A nu cube and e power minus beta nu by T. Okay. So A and B are empirical formulas. So this Wien's law is fits at high frequency but fails at low frequencies. This is valid at high frequency and failed at low frequencies. I will try to explain all this in next slide. I will try to explain all this in a graph. Okay. So Wien's formula fits at high frequency but fails badly at low frequency. This is an important statement. Okay. So we can expect this type of questions in your junior lecturers and degree lecturers exams. Okay, because these exams will have some theoretical questions also. Wien's formula fits at high frequency, otherwise high frequency, low wavelength. Both are same, right? So this is Wien's law is valid at this place and fails at low frequency or high wavelength. So both ways we can expect questions both ways, either in terms of wavelength or frequency. Next. So remember the formula. Energy density is proportional to exponential decay of nu. Okay, you remember this thing. And as a function of temperature. And this is an empirical formula. Sometimes this empirical formula will be like Boltzmann constant. K, 1 by K. Okay, right. And Rayleigh's energy distribution function. In 1900, Rayleigh tried to explain the energy distribution function. Tried to explain the distribution of energies. So the radiation inside the cavity to consist of standing waves and nodes at the metallic surfaces. So for example, this is your cavity and it has some hole here and you are trying to send the radiation through this one. Okay, and whatever be the radiation entering through this hole, it will make so many reflections like this, and we can say finally that the radiation is trapped inside this cavity. And according to Rayleigh, he considered that the radiation inside the cavity forms standing waves. with nodes at the metallic surfaces. So what it means the standing wave? For example, if we have a wall and a string is fixed between these two walls, and if you pluck it, then you will get a progressive wave like this. It will go like this, and after some time it will come back. So such type of waves are known as standing waves. So according to Rayleigh, so he assumed that the radiation inside the cavity forms standing waves like this. So I can take, this is my cavity, I can treat this is my cavity. At the walls of the cavity, the radiation forms a node. So this is node and this is antinode, and this part is node. Node means amplitude is 0, like that. Next, these standing waves are equivalent to harmonic oscillators, and the number of modes of the radiation is given by this expression. N of nu is equals to 8 pi nu square by c cube, and the energy density is related to this expression. Here I am not going into the details. How will you get N of nu into E? Okay, so number of modes multiplied by the average energy of the oscillator, so we'll get this expression according to the equipartition theorem. That means according to the classical thermodynamics, the average energy of harmonic oscillator is given by this expression. Average energy is given by kT. So Rayleigh made a mistake in assuming this quantity only. He thought that all the harmonic oscillators inside the cavity will have same energy, that is kT. How many oscillators are there? For example, we have n charged oscillators. Each oscillator will have average energy kT. So that was his mistake actually. Okay, so he gave this expression 8 pi nu square by c cube correctly, but he failed to define this E, expectation value E, average value E. He failed to give the exact expression. So when you substitute this expectation value E, that means average energy value, so he derived a formula, and this is the formula. The energy density of a black body, the energy emitted by a black body per unit frequency, is given by 8 pi nu square by c cube into kT. So this is also proportional to temperature T. Okay, so this law is valid at low frequencies and failed at high frequencies. This law is valid at low frequencies and failed at high frequencies. Now, so Planck's energy distribution function. In 1900, Planck started the experiment. So Planck started working on the Rayleigh's law. So he focused on the important thing, that is the expectation value. What is the average energy of an oscillator? So he worked on this one. Okay, so according to Planck, he considered that energy exchange between the radiation and the matter must be discrete, whereas Rayleigh considered that energy exchange between the cavity, walls of the cavity and the harmonic oscillators is continuous. So that is the mistake made by Rayleigh. Whereas Planck considered that the energy exchange between the radiation and matter is discrete. He postulated that the energy of the radiation emitted by oscillating charges must come in an integral multiple of h nu. So he gave a quantization rule. E is equals to nh nu, where n is equals to 0, 1, 2, 3, 4 and so on. Okay, and what is the formula for energy density? So this is the formula for energy density. 8 pi, what is this, nu square divided by c cube, the number of moles, and average energy of the harmonic oscillator. So Rayleigh assumed that all the oscillators have same average energy kT, but Planck thought that the energy exchange between the radiation matter is not continuous and discrete. So instead of integration, he uses summation here, right? Summation means discrete basis system. If you use, so this is discrete. So the summation represents that the whatever with the expectation value we are trying to calculate over the discrete basis only. So he got h nu by e power h nu by kT minus 1. If you integrate the same function, you will get only kT. But if you apply the summation, you will get h nu by e power h nu by kT minus 1. That means the radiation and matter exchange energies in the integral multiples of h nu only. So that is the main assumption, so given by Planck. By using this expression, by substituting this expression value, so you can expect the energy density value 8 pi nu square by c cube into h nu by e power h nu by kt minus 1. Okay, and if you want to write in the wavelength format, this is the formula. So how to derive this wavelength formula? How to derive the energy density in the form of wavelength? Let us try to here. So energy density means energy per unit volume. So this is energy density. Energy per unit volume per unit frequency. So now I want to calculate energy value only. Okay, so energy value means I should multiply with d nu. So let me write here 8 pi nu square c cube h nu divided by e power h nu by kt minus 1 du nu. So what is the relation between nu and wavelength? The frequency is related by c by lambda. So if you write d nu, it can be like c by minus lambda square d lambda. So I want only positive values, so I can take modulus here. So simply it is c by lambda square and d lambda. That means wherever there is d nu, you can write c by lambda square d lambda here, and wherever nu is there, you can write c by lambda square. So substitute the formulas on the right hand side. Let us try to look what will you get. Okay, so I am trying to substitute here on the right side. That is 8 pi nu is what? C by lambda here, and it is a square, and divided by c cube is there. H nu and c by lambda is there, and in the denominator you can write e power h c by lambda kt minus 1 and d nu. So write c by lambda square d lambda. So if you simplify this one, you will get this expression only. So students, this is very important. Sometimes in exams they will give questions in terms of wavelength. They will ask questions about the energy density in terms of frequency, sometimes in terms of wavelength. So you must be familiar with these two expressions, how to convert one from another. In other words, if I want to ask, I am explaining this point particularly in point of this DL and JL exams. So for example, if I give an expression in terms of angular frequency, which of the following expression represents the energy density given by Planck's? So how will you change this expression in terms of angular frequency? So angular frequency is written as 2 pi nu. Okay, so wherever frequency nu is there, I can substitute omega by 2 pi, and similarly d nu is there, so that is d omega by 2 pi, and made changes, you will get third expression in terms of energy density in terms of angular frequency and temperature. So you can do this type of exercises. Okay, before going to your exam, before attempting the exam, you just check yourself whether you are able to convert all these parameters from one set to another set or not. Okay, yes. So this is the experimental data. First of all, the energy density U as a function of frequency. So the energy emitted by a black body per unit volume per unit frequency is obtained by doing experiment like this. Okay, and the theoretical formula given by Planck's is exactly fitting this data. So experimental data and theoretical data both are matching here. See, on the left side, this is Rayleigh-Jean's law. So Rayleigh-Jean's law is valid for low frequency ranges only. So on the x-axis, the range of the frequency is 10 power 14 hertz. So in this range, below 10 power 14 hertz, the Rayleigh-Jean's law is valid here. In the high frequency ranges, you are getting an exponential value, right? You are getting an infinite value. So Rayleigh-Jean's formula is valid in the low frequency range, failed at high frequency range. The same way, Wien's displacement law is valid at high frequency range and failed at low frequency range. In the high frequency range, Wien's displacement law, you can see that exponential decay, because in Wien's distribution law we have exponential factor also. So at high frequency, Wien's law is valid at high frequency range. In opposite case, in terms of wavelength also you can write. So now, so I want to generalize the Planck's radiation law. So we can apply the Planck radiation principle for any black body. And when you take the low temperature, for example, I want to check the Planck's radiation law at low frequency and high frequency range. Okay, so at low frequency range, Rayleigh-Jean's law is valid. So Rayleigh-Jean's law is exactly fitting with the experimental data at low frequency range. Whereas at high frequency range, you should reach Wien's displacement law. So now here I am trying to check whether the radiation law given by Planck is giving this behavior or not. Okay, so now let us look at the low frequency. When low frequency means h nu is less than kt, very less than kt, then in that case I can write e power h nu by kt, e power x can be written as 1 plus x. Simply I can write like this: if x is less than 1, not less than 1, it is very less than 1, then I can simplify, I can made assumption that e power x is equals to 1 plus x. Okay, so now write down the energy density function. U of nu comma t is equals to, what is the formula? 8 pi h nu cube by c cube and 1 over e power h nu by kt minus 1. So this is the formula. So substitute all these values here, substitute that exponential value. What will you get? Let us check here. So 1 is there. E power h nu by kt can be written as 1 plus h nu by kt, and already there is 1. So 1 get cancelled and kt will go to the numerator, and what will you get here? 8 pi h nu c cube, and the denominator you have n h nu, and kt will go to the numerator. So from this I can see that h get cancelled and 1v will get cancelled here, you will get square. So finally I can write h 8 pi nu square by c cube. So what is this? The number of modes of a standing wave, the number of modes of an harmonic oscillator into kt. What is this kt? This is the average energy of an harmonic oscillator given by Rayleigh-Jeans. That means from this Planck's radiation principle at low frequency, the Planck's radiation principle, the Planck's radiation law is same as Rayleigh-Jeans law. Okay, so that means I can derive Rayleigh-Jeans law from Planck's radiation principle at low frequency range only. So I am writing here Planck radiation law is giving rise to Rayleigh-Jeans law at low frequency. Okay, so you will get a theory question in exams, even in your CSIR, JEST, or in competitive exams, state level exams. So you will be asking this type of questions. So at low temperature, at low frequency range, Planck's law reduces to Stefan Boltzmann law, Wien's displacement law, Wien's law, or Rayleigh-Jeans law. So you have to identify that one. So what you have to do? So you have to make this assumption h nu very less than kt. In that case you will get this one. Now when h nu is greater than kt, then what happens? So e power h nu by kt will be very larger than 1. Since x is greater than 1, x is very greater than 1, then e power x will be greater than 1. In that case, let me write the energy density. So this is the energy density formula, 8 pi. So here what we have, h nu cube divided by c cube, and look at the denominators. So e power h nu by kt is greater than 1. So I can ignore the 1 here. So I can write 1 by e power h nu by kt. So minus 1 is I am ignoring because this value is very more. So I can write 8 pi h nu cube by c cube. Take this value into the numerator. What will you get? E power h nu by kt. So this is nothing but your displacement law, right? Wien's displacement law. So this is proportional to nu cube and e power minus beta nu by t. So from this we can find the parameter. What is beta? H by k is your beta, and what is a? 8 pi h by c cube is your a. So this is Wien's displacement law. Sorry, Wien's law, not displacement law, Wien's law. This is Wien's law of energy distribution. So that means Planck's law is reducing to Rayleigh-Jeans law at low frequency, and it is following Wien's law at high frequency. In terms of wavelength, if I want to discuss in terms of wavelength, Planck's law reaching Rayleigh-Jean's law at high frequency, high wavelength range, or Planck's law is reducing to Wien's displacement law at low wavelength. Okay, and there is another thing. If we integrate the Planck distribution function over the whole spectrum, so this is the expression here. So this is energy density, and I want to integrate the distribution function over the whole spectrum 0 to infinity. What will you get? If you look at this one, finally you are reaching at Stefan Boltzmann law, sigma t power 4. Okay, that means we can deduce Rayleigh-Jean's law, Wien's law, and Stefan Boltzmann law. So I can say that the Planck's law is suitable to describe the energy radiation of any black body. Okay, so this is exactly matching with this experimental data. You will get Rayleigh-Jean's law at low frequency and you will get Wien's law at high frequency. If you integrate over the whole energy spectrum, so finally we are reaching at Stefan Boltzmann law. Okay, I hope you understand this thing. Next, let us work on one of the example, one of the previous question. So this is CSIR June 2014. It's a very simple question. Which of the following graphs gives the correct qualitative behavior of the energy density of the blackbody radiation of wavelength at two temperatures, T1 and T2. T1 is less than T2. So in the beginning slide, I have shown a diagram, right? Energy density as a function of frequency. So this is the experimental data. Let us say this is temperature T1. If you increase the temperature, so this is T2 and T1 is greater than T2. So T2 is greater than T1. T2 is greater than T1. Then what happens? The peak value shifts towards the right. If your x-axis is the frequency, the peak value shifts towards the right. Okay? If you want to do the same thing, in case of wavelength, the peak shifts towards the left. That is the thing. So condition is T1 less than T2 or T2 is greater than T1. No problem. T2 is greater than T1. Look for this one. So here energy density as a function of this one. So we got two different values, but this is not correct. And look at this diagram. T1 is this one, T2 is this one. So the peak is shifting towards the right, but the wavelength here x-axis is the wavelength. So this is not correct. If it is frequency, then it is correct. But this is the wavelength. And look at this one. So T1 is here and T2 is here. So the peak value of wavelength is shifting towards left. So I can say this is the correct answer. Okay, so which of the following graph gives the correct qualitative behavior? So option C is the correct one. This is CSIR June 2014. This is simple, right? Right. Next question. Okay, TIFR 2015 question. This is something related to this energy density. Same question. Two black bodies radiate energies T1 at temperatures T1 and T2. T1 greater than T2. The condition is, don't get confused. T1 is greater than T2 here. Okay. If you increase the temperature, the peak will shift. The energy emitted per unit time, per unit solid angle, per unit surface area of black body in the frequency range nu to nu plus d nu is given by this one. Which of the following graph has the correct form? This is just like energy density only. If you use the solid angle, that means energy emitted per solid angle is your radiance, and energy emitted per unit time, per unit area, per unit frequency, you can call it as energy density. Okay, which of the following has correct form? So you know that graph, right? If temperature is increased, the peak value will shift towards the right. So this is looking somewhat correct. T1 is here, the peak value of the frequency is here, T2 is here. But what is given here? T1 is greater than T2. That means temperature is decreased. So here this is not correct, since the condition he gave in the T1 greater than T2, and this is not correct, and this is also not correct. This one will be correct, since this is T2 at low temperature, and if you are increasing temperature, the peak value will shift towards the right. This is the peak value of the frequency at T2, and when you increase the temperature, here T1 is more, right? So peak is shifting towards the right side. So which one is the correct answer? Option D is correct answer. This is very simple, and you can solve these questions within less than 2 minutes or 1 minute also. These are time saving problems. So there is one other formula, another law, that is means displacement law. I will discuss this one. So Wien's displacement law tells that the maximum of Planck energy density occurs for a wavelength of the form lambda max is equals to b by t, or I can say that the maximum peak value of the wavelength and the temperature is constant. So this is a statement of Wien's displacement law. This law is used to calculate the energy of the stars. Okay. So lambda max is equals to b by t. B is 2898.9 10 power minus 6 meter Kelvin divided by temperature T. Okay, so what is the physical meaning of this Wien's displacement? Okay, first let us start with this energy diagram. Energy density as a function of wavelength. Okay, so let me start when the temperature is 2000 Kelvin here. So this is the peak value, students. 10, what is the 1, 1.1, 1.2, 1.3. So at 1.2, around 1.2, I have lambda peak. Okay, so lambda max is 1.2 micrometers when temperature is 2000 Kelvin. If you increase the temperature, the peak value shifts towards the left. The temperature is 300 Kelvin, the peak value is like 0.9 micrometers. Okay, so we said that the product of lambda max and the temperature is constant for the entire black body spectrum. So you can multiply here 2000 into 1.2, you will get same value, and multiply 3000 into this value, you will get same value. Similarly, you multiply 5000 into what is the lambda peak value here, you will get same constant value, and that constant value is 2898.9 10 power minus 6 meter Kelvin. Okay, so this is Wien's displacement law. So the maximum of the Planck's energy density occurs for a wavelength of the form lambda max is equals to b by t, or lambda max into t is equals to constant. So let us do one problem here. Estimate the surface temperature of a star if the radiation it emits has a maximum intensity at a wavelength 446 nanometers. In this question, he is asking that calculate the surface temperature of a star. So we have to calculate T if it emits the radiation at a wavelength of 446 nanometers. So lambda is given, lambda max is given 446 nanometers, 446 into 10 power minus 9 meters. So you know B constant value. What is the B? B is a constant 2898.9 10 power minus 6, and lambda max is given. Just you can simply calculate T. Okay, so T we can calculate from the expression. And what is the intensity radiated by the star? So what is the intensity radiated by the star? You can calculate simply by using Stefan Boltzmann law. Okay, so this is the temperature. T is equals to B by wavelength 446 into 10 power minus 9 meters. So you will get approximately 6500 Kelvin. So here you should focus on the answer itself. So you know the formula, right? So I am looking at the result. So what is the temperature of the star? The temperature of the star is around 6500 Kelvin. Okay, this is a huge temperature. Okay, next. And he is asking the intensity radiated by the star. Intensity is what? Power by area. And that is A into sigma T power 4. So here I can consider that if A is given, that's well and good. Otherwise, I can take A is equals to 1. I will treat that star as a perfect black body. So sigma T power 4. What is the sigma value? 5.67 10 power minus 8 watt meter power square. Watt per meter square per Kelvin power 4 into T value is 6500 Kelvin, and you will get this much of energy, this much of intensity. Look at this intensity. 101.2 10 power 6 watt per meter square. Generally in household purposes we use 60 watts bulb only. So how much intensity we'll get, how much heat we can get from the 60 watt bulb? 60 watt or 100 watt bulbs. Look at this one value, this one. So this is like 100 million watt energy. So this much enormous energy is released from the sun or from the star. This enormous intensity will decrease as it spreads over the space. So that is the thing, and I want to finish this session by solving this problem. So this is the same problem. This is I think it's a CSR problem. So the graph in the below figure shows intensity as a function of frequency of a perfect black body fixed at frequency. So I told you that intensity, energy density, pressure, radiation pressure, and what else, all are proportional to t power 4, and they have similar behavior. This is like this. Okay, a bell shaped energy distribution curve. So this is like just like a Gaussian distribution function. Okay, so what is the question here? The corresponding graph at at a temperature 2T can be obtained by which of the following operations? So this is the graph when when the temperature is equals to T. Now he is asking what is the shape of the graph when T is equals to 2T. So this is when T. What happens when temperature is changed from T to 2T? So he gave the options. Multiply the frequency coordinate by 1 by 2 and the intensity coordinate by 8. Multiply the frequency coordinate by 2. Multiply the intensity coordinate by 8, like that. 1 by 2, 16 to 16. So I don't bother about the answers. First I will write the formulas. He is asking about nu and intensity. So you know the formula, right? Intensity is proportional to T power 4. So if he don't mention that the dimension is 2 dimension, 3 dimension, or 1 dimension, you can simply take intensity is proportional to T power 4. Okay. So this is the one case, and now he is asking the second case, what happens to the intensity when temperature is changed to 2T? So what will happen here? So that intensity is changing to 2 power 4 is how much? 16 times of T power 4. So the intensity will change 16 times. Do you have the thing here? Multiply the coordinate I coordinate by 16. We have one option here. Another option is there. Multiply the coordinate by 16. So out of these two, we have to select the correct one. Next, what is the relation between frequency and the temperature? You know the relation, right? Lambda is proportional to B by T or 1 by T. This is one relation. And you can write lambda is C by nu, and I can write 1 by T like this. So I am trying to relate the relation here. So ignore the constants. So frequency is proportional to the temperature. So the second case, what happens to the frequency when the temperature is 2T? That is the question, right? So what happens to the I and nu values when T is changed to 2T? So what is happening here? 2 times of the initial frequency. So you have to multiply the x-axis, you have to multiply the frequency by 2. Look at this one. So this is the case. You have to multiply the frequency coordinate by 2 and intensity coordinate by 16. So D is the answer. So this is, look at this question, look at the answer, how simple it is. So in the most of the exams, they are asking the questions like this only. Okay, so temperature dependence on intensity, energy density, specific heat, entropy, all these things. They will give one temperature and they will ask at another temperature values. They will ask all these parameters at T is equals to 2T, 3T, 4T, or 3 by 2 or half T, like that things only. Okay, thank you for your attention. Thank you very much. If you like the video, please share the video and follow the link given below, and try to subscribe our Nature Academy. Thank you so much.